Alright, so let's talk about seawater chemistry now. Seawater chemistry is everything on Earth is made up of elements. Elements are the most basic form of a chemical that you can have. And a chemical can no longer be broken down if it's an element. So for instance, if you have water is made up of two different elements, your hydrogen element and your oxygen element. And when they combine, you create a molecule. But when they are individual, say you have an individual hydrogen, a hydrogen can not be broken down any further. And so these elements are what interact with each other and create chemical reactions. Here's just a pretty basic table, periodic table, and this table here categorizes all of the elements that we have here on Earth. Some of them occur naturally, and some of them are radioactive and can only be made within a lab. So all of the ones that are down in the hundreds, so like 100, element 100, and 101, 102, 103, and all of those that are 113, 114, all of those are radioactive and need to be created in a lab. They have such a short lifespan that they can't occur outside of that. But all the ones that we're accustomed to, like carbon, nitrogen, oxygen, those ones occur naturally, obviously. Our atmosphere is made up of 21% oxygen and 79% nitrogen. So those are the two main ones. But water in the ocean, that is made up of hydrogen and oxygen. Right? Okay, so let's look at an atomic structure. An atom, or basically an element, is made up of three different components. You need a proton, neutrons, and electrons. Okay, and these atoms or elements are the basic building blocks of everything here on Earth. And you can see the image on the right hand side there. In your nucleus, you contain your neutron and protons. Your neutrons don't have any charge. They're neutral in charge, but they do add weight to the molecule or the atom. And your protons, they have a positive charge, and generally speaking, they will you will have the same number of protons as well as neutrons and electrons in an atom. And then your electrons have the negative charge, and they are floating around outside of the nucleus. So they have what's known as valence shells, which we'll cover in a little bit. But essentially, when we draw electron valence shells, they're these nice circles around the nucleus, but that's not really the case. Really, what happens is they kind of just float around in this area around the nucleus, and the electron can be anywhere, as depicted by this comic strip right here. They don't just circle around the nucleus in a nice orbit. They can be anywhere within that surrounding area of the nucleus, which kind of makes it difficult to map them out. But for science purposes, for demonstration purposes, we'll just show them as a nice, neat orbit around the nucleus. So let's look at electron shell configurations. So in the nucleus, again, you have your proton and your neutron. I apologize, hydrogen should have a neutron in there, but hydrogen should have one proton and one neutron within its nucleus, and it will have one electron in its outer shell. And then when we look at helium, which is number 2, helium will have 2 protons and 2 neutrons in its nucleus, and it will have 2 electrons in its outer shell. But when we get up to higher level elements like carbon, for instance, carbon will have 6 protons and 6 neutrons in its nucleus, and it will have 6 electrons in its outer shells. But if you notice, it has 2 shells, unlike helium, which only has 1. And that's because that inner shell that you see for carbon can only hold 2 electrons. So only 2 electrons can be in there at a time. And so then the other 4 need to go into a second shell. And in this particular shell, it can hold up to 8 electrons. But carbon only has 6, so its outer shell will only hold 4. So let's look at some different things that you can use to characterize these elements, and one of them is the atomic number, which is essentially just the number of protons in its nucleus. And when you look at the periodic table, the atomic number characterizes what element it is, and that number is in the top right hand corner, as you can see in the right hand image circled in red. And this atomic number will never change. So a helium element will always have 2 protons. If for whatever reason it has 3, it's no longer helium, it's a lithium element. So this is how you can identify different elements, because they will always have 6 protons if it's a carbon, or 7 protons if it's a nitrogen. That number will never change. Okay. And next we have atomic mass, or atomic weight. And this is essentially, you need to add the number of protons and the number of neutrons in the nucleus. And so in this case of helium, we have 2 protons. It should have 2 neutrons. And so its atomic mass should be 4. Okay, so in the sense of carbon, carbon will have 6 protons and 6 neutrons, so its atomic mass will be 12. And that's the number on the bottom under the symbol. So for carbon, it's underneath on the bottom of the square. It should say 12.1. Alright, so let's take a look at this carbon atom. Can you tell me how many protons, how many neutrons, how many electrons, what's its atomic number, and what's its atomic mass would be? Okay, so take a few moments, answer that. If you came up with 6 protons, 6 neutrons, 6 electrons, the atomic number being 6, and the atomic mass being 12, then you are correct. Alright, so you should have 6 protons. The neutrons should be the same as protons, as well as the electron. The atomic number is just a reflection of the proton, so it should be 6. And for the atomic mass, you just need to add the protons and the neutrons together. So that's 6 plus 6, which gives you 12. Isotopes are interesting because they are still the elements that you are talking about, but they may have different neutron numbers. So in this example right here, I have oxygen. Oxygen has 2 isotopes that are stable and have a balanced charge and occur naturally here on Earth. Oxygen 16, which has 8 protons and 8 neutrons, is the normal and the most abundant oxygen element that we have here on Earth. But you also have oxygen 17 and oxygen 18. Now, oxygen 17 has 1 more neutron than 16, and oxygen 18 has 2 more neutrons than 16. Interesting fact, oxygen 16 is what you would find normally here in the tropics, so here in Hawaii. Oxygen 18 is what you would normally find is in higher concentrations in the polar regions. And that's just due to the fact that it's heavier and it has less ability to go up into the atmosphere. So yeah, when you're talking about isotopes, it has the same number of protons, same number of electrons. It may have a different number of neutrons in its nucleus. So oxygen 18 definitely will be heavier than oxygen 16. Now, if we talk about ions, ions are a little bit different. Ions will not have a balanced charge. They will either have a positive or a negative charge depending on whether they gained or lost an electron. And in this example right here, we have sodium and chlorine. Sodium has 11 electrons, and in its outer electron shell, it only has 1. Chlorine, on the other hand, has 17 electrons. And because that outer shell is missing 1 electron, it could add 1, and these elements would prefer to have full electron shells. So that extra one that sodium has and that missing one that chlorine has, they would prefer to fill it. So what happens is sodium will take that extra electron and say, "Here, chlorine, I'll give you my extra electron to fill your shell, and then now I have a full shell because I don't have that outer third ring anymore." So when you look on the right hand side of that image, sodium has lost an electron, so it becomes a positive charge or cation, and chlorine has gained an electron, so it becomes more negative and it becomes an anion. And now, because they gave that sodium gave that electron away, you have these two charges that are attracted to each other, and they become sodium chloride. All right, so we'll talk about this ionic bond between sodium chloride in a little bit later. So some examples of ions that we have in the ocean are hydrogen, potassium, fluoride, calcium, nitrogen, and phosphate. So you can see they have different charges. Hydrogen obviously is a positive charge, so is potassium. Fluoride is a negative charge, much like chlorine. Calcium is a 2 positive charge, so it lost 2 of its electrons, whereas phosphate lost or gained 3 electrons. So you can see some of those examples right there, and all of these are really important in the ocean and for the different organisms in the ocean. Now, if we talk about molecules, so what we've been talking about so far are specific elements, and they are just single elements. But when you combine multiple elements or atoms together, you get a molecule. And in order to combine 2 or more atoms, you need to have a bond between them. And so, for instance, here are just some examples of molecules here on Earth. The most obvious is oxygen and nitrogen, right? Ammonia, carbon dioxide, water, methane, and glucose. These are very common molecules that we experience here in oceanography and marine biology. So, and those molecules that we just talked about have different types of bonds, right? But one thing that makes water in particular very special is that it's a really good solvent. Now, what do I mean by solvent? A solvent just means that something that can dissolve another molecule. So water, let's take salt for example. Water dissolves salt very, very well. And because salt is ionic, so salt has that positive and negative charges associated with their elements, water can pull apart the individual sodium and chlorine atoms from salt and dissolves that salt into water. So you, instead of getting just the salt grains, you get salty water. And that's because of this electrostatic attraction between the charges in the salt and the dipole of water. So let's look at water's thermal properties, because this is basically what makes it very special here on Earth. Water, unlike other molecules, has all three phases present on Earth. So water, you can find water as solid, which is ice, right, in the polar regions. You can find it as liquid, and you can find it as gas. And they can occur, and all three of them can occur at the same time on Earth's surface, which is really interesting. So if we look at this phase diagram of water, you can see that the triple point, which is at A, is at 0.01 degrees C, and so because the triple point is at a pressure and a temperature that can be found on Earth's surface, that allows all three phases of water to occur simultaneously. So when you look at phase diagrams for other chemical or other molecules, that triple point doesn't occur naturally. A lot of times it has to be created in a lab, and a lot of times you'll either see solid and maybe liquid present on the Earth's surface, but not gas, or vice versa. But essentially, the reason why all three phases are able to exist on the Earth's surface is because of that triple point, and it influences Earth's heat budget. So because you can have solid, liquid, and gas in the polar regions, because you have a lot of ice, it tends to be colder up in that area, and in the near the equator, you tend to have a lot more heat because of the sun, so it causes more water vapor to exist in the atmosphere, and because of the ocean's currents, it moves that warm water up to the polar regions from the equator and warms up the polar region so that it doesn't become too cold. So there's that. And just really quickly, let's look at the three states of phases of water. So you have gas on the right hand side, you have liquid in the middle, and you have solid. So your solid is going to be a very rigid shape. It's going to have the molecules are going to be very defined and very crystallized, whereas liquid water, the molecules are just freely moving around. They're a little bit more condensed than they are in gas, but still yet they will conform to whatever container they're in. Now let's look at this density and temperature chart. And what's really interesting about water is you would think that solid would be the most dense out of the three phases. But in reality, it's water that's the most dense, or liquid water that's the most dense. And when we look at this density chart, you can see that gas is the least dense, right? And then as the temperature cools down and you go from gas to liquid, and when that liquid cools down even further, at the point at which it gets to 4 degrees C, that's when it becomes the most dense, because the molecules are coming together, you're starting to form crystalline shapes, but they haven't completely formed yet. And then once you continue to cool and you get closer to zero, when you start to form ice, that those molecules start to spread apart to create that nice crystalline shape that you see in ice, and it loses some of its density. So that's the reason why those ice cubes that you put in your drink float on top of water. So let's just summarize some of what I've talked about. So at 4 degrees, as water cools down to 4 degrees C, the molecules slow down, water expands, water contracts, and the molecules come together, closer together, and you're increasing your density because those molecules are coming together. Now, once it hits 4 degrees C, and it continues to cool, those hydrogen bonds between the water molecules are forming. So it spreads apart, forms those crystalline, starts to form those. So as water cools below 4 degrees C, those hydrogen bonds start to form and the water starts to expand because that crystalline structure is starting to create, be put together. And then as water hits 0 degrees and freezes, that water has expanded to 9% its original size. So you can see the photo on the right hand side there. And your density decreases because now you have those nice crystalline structures and they're all evenly spaced out apart from each other. And that loses that density that it was at when it was at 4 degrees C. So here are 4 different properties of water that we'll be talking about now. The first one that we'll talk about is high heat capacity. Then we'll talk about high heat vaporization. Then we'll talk about surface tension. And then we'll talk about the polarity and its ability, water's ability to act as a really good solvent. So let's look at heat capacity first. Now water has a high latent heat, and that just means that it can store and release heat from it, and it can store a lot of heat, as we'll see in a second. And because it can hold a lot of latent heat, that leads to its ability to have a really high heat capacity. So let's look at this image below. If we start down at the bottom, in the bottom left hand corner at 0 degrees, or 0 degrees, below 0 degrees at negative 40 degrees and 0 calories. If we heat up that block of ice up to point A, and then when you look from point A to point B, it takes 80 calories per gram in order to melt a block of ice into liquid water. Okay, and then if we continue heating up that liquid water, you can see it takes another 540 calories per gram to turn all of that liquid water into water vapor. So you can see the difference. It doesn't take very much heat at all to change a block of ice into liquid water. That's why when you have that nice cold drink and you have ice cubes in it, it doesn't take too long before those ice cubes melt into the drink. But if you were to continue to leave that drink on the table and wait to see if all the water evaporates from that drink, it'll take a lot longer for that water to evaporate into water vapor. And it's because it requires much more heat. So when you put that pot of boiling water onto the stove, it takes a little bit before it starts to boil. So let's look at specific heat, because depending on what molecule you're looking at, what sort of material you have, it will have different specific heat. So heat capacity is just the amount of heat required to raise the temperature of 1 gram of substance by 1 degree C. So if we look on the right hand side at that graph there, you can see that water, pure water, now this is a distilled water, it doesn't have any minerals or anything else in it, has the highest heat capacity, specific heat capacity, right? At 1 calorie per gram per degree C. Versus if we take ice has half the specific heat capacity as pure water. Okay? And specific heat just refers to the heat capacity per unit mass. So, and then if you look at the graph again, you can see all the way at the bottom, mercury doesn't have a very high specific heat capacity at all at 0.03, and that's for liquid mercury. So here are just a summary of some different properties of seawater. the heat capacity for seawater decreases with increasing salinity. So the higher the salt concentration is of the water, the less heat that water can hold, and that's because the water has more salt molecules and it has less space for heat to be stored in the water. And evaporation occurs more slowly in fresh water. So when you have a higher salt concentration, you'll have a higher evaporation rate, and that's because you have more salt molecules in there that's breaking apart the hydrogen bonds between the water molecules, so evaporation occurs much more quickly. Specific gravity, that just means what is the density of your material. So pure water has a density of 1 gram per cubic centimeter, and seawater at 2 degrees C has a density is a little bit more dense at 1.028 grams per centimeter cube, and that's just because it has more salt. So there's more molecules in the water itself. And seawater's boiling point, as you increase salinity, you increase the boiling point. Now, if you increase salinity, you decrease the freezing point. So this is why seawater tends to act as a antifreeze, in the sense that you need to take out more heat from the water in order to cause it to freeze. So those water molecules, when you increase the amount of salt in it, those salt molecules are in the spaces in between the water molecules. And when you start to form the crystalline shape for solid water or for ice, those salt molecules in a sense get in the way. So it slows down the freezing process of seawater. And so seawater won't freeze until negative 2 degrees Celsius, whereas fresh water will freeze at 0 degrees Celsius. So it takes just a little bit longer for seawater to freeze. Now, solutes are essentially the materials that are dissolved in water. And so water is a solvent, and salt in the ocean, salt would be the solute. And so let's look at the pie chart on the right hand side there. You can see in 1 kilogram of seawater, majority of that kilogram of seawater is water, but there's a small fraction of it that are solutes. And when we look at the larger pie slice there, you can see that the solutes that are in seawater, majority of them is chlorine and sodium. And you have some others that are sulfate, magnesium, calcium, potassium, and some others that are make up a smaller chunk. Now, all of this is within that small little green sliver. So these ones essentially contribute to the salinity of seawater and making the water salty. And in order to measure salinity, we have devices, and they express the total amount of dissolved salt in water in parts per thousand. So here on the next slide, you can see these are just some of the major solutes within seawater. You can see sodium and chloride are the two top components of solutes within seawater. They make up more than half of the total. But then you see the other ones that also contribute and are important not only for seawater chemistry, but for biology within the ocean as well too. So we have processes that affect salinity in the ocean. So these four processes decrease seawater salinity. So precipitation, whenever it rains over the ocean, you're introducing fresh water, and that decreases salinity. Same with runoff, you're basically just taking fresh water from land, putting it into the ocean, which will therefore decrease salinity. And then icebergs and sea ice melting, that also decreases seawater salinity. And then when you form sea ice or when you have a lot of evaporation from the sun, those are processes that can increase salinity. So here are just some examples of salinities from water bodies around the Earth. You can see that normal average open ocean salinity ranges anywhere from 33 to 38 parts per thousand, and this just depends on where you are in what ocean basin. But you can see there are places that are not as salty as the open ocean, like the Baltic Sea, which is at 10 parts per thousand. Or you can have places like the Red Sea, the Great Salt Lake, and the Dead Sea that are more salty than the open ocean. So if you were to go to the Dead Sea and take a dip, you probably wouldn't be dipping, but you would more so be just floating on top of the Dead Sea. Because of how much salt there is, it increases your buoyancy within the water, so to the point where you're basically floating on the Dead Sea at that point. But tap water and bottled water, those are examples of lower salinity waters. And so tap water does have a little bit of salinity within it, and that's primarily due to the water going through the piping. It picks up some solutes as it goes through. And then bottled water also has a little bit, and that's mainly for preservation while the bottle is on the shelves waiting to be bought. On this slide here, we see a global map of surface water salinity, and you can see the reddish colors are higher salinity, whereas the bluer and pinker colors represent lower salinities. And you can see that the Atlantic is more salty than the Pacific. And that's partially because a lot of the cloud cover and rain that is created in the Atlantic gets blown into the Pacific. So essentially the Atlantic is losing its water to the Pacific. But it's all a cycle. Currents move water all over the place. So even though it is losing water to the Pacific, it is gaining water through the currents as the currents flow around the Earth. Now, that was an image of surface water salinity, but let's look at where on the Earth you are will determine what sort of salinity profile you'll have. So for instance, in higher latitudes, which is the polar regions, you'll tend to have lower salinities. And that's primarily because you'll have more precipitation, you'll have active sea ice melting, and you have a lot of runoff. Whereas low latitudes by the equator, you'll tend to have lower salinities and higher precipitation rates because of how air masses in the atmosphere are interacting with each other. So high latitudes and latitudes near the equator will have lower salinities because of the increased precipitation, but mid-latitudes in between the equator and the polar regions, you tend to have higher salinities because this is where you have warm, dry air, and you have more evaporation. So you tend not to have a lot of precipitation within these areas. So here's just a graph showing the same thing. You can see the red line is temperature. Temperature is pretty even a pretty even curve as you go from North Pole to South Pole. So it decreases at the polar regions, increases in the equator, and decreases as you get down to the South Pole. Whereas the green line shows salinity, you can see it has two humps, almost like a camel's back. When you start at the North Pole, you start off at a very low salinity, then you increase as you get closer to 30 degrees north, and then you start to decrease again because of the increased precipitation at the equator. You'll increase once you get back to 30 degrees south, and then you'll decrease once you get back to the South Pole region. So that was surface salinity and how it varies depending on what latitude you're at. But let's look at salinity variation with depth in the ocean, because depending on what latitude you're at will depend on what the salinity variation is at depth. So when you're near the equator at low latitudes, you'll tend to see that salinity decreases with depth. Now this depends on where you are near the equator, but in general, you'll tend to have higher salinities at the surface than in the deep ocean. And this is in contrast to the polar regions and the high latitudes, where you tend to have lower salinities at the surface and higher salinities at depth. And so if we just say the average salinity at depth is about 35 parts per thousand, you can see the graph there. At polar regions, you'll see 33 parts per thousand at the surface waters, and you'll see 37 parts per thousand at the surface waters near the equator. And that pinkish orangey color between 200 meters and 1,000 meters is what's known as the halopine. Now you can see the curve, the salinity curve changes in this area, and that's essentially what that means. It's the area at depth where you see the greatest change in salinity. And so you can see at the high latitudes in the polar regions, you'll see it goes from low salinity to high salinity, and the area where there's a rapid change, that's where you have your halopine. And so seawater density will change depending on what's going on. So if you are decreasing your temperature, you will increase your density. And so that's much like what we were talking about earlier, where as water temperature goes to 4 degrees C, it decreases to 4 degrees C, you're increasing the density because you're moving those water molecules closer and closer to each other. You're decreasing the space in between the water molecules. So you tend to increase your density that way. And out of all three of these points right here, temperature has the greatest influence on water density. You can also increase your density of seawater by increasing salinity. So those spaces in between the water molecules, if you increase your salinity, you're putting more and more salt molecules into those spaces, and therefore you're decreasing the amount of space in between the molecules. Therefore, you're increasing your density. And then you can also increase density by increasing pressure. So if you push those water molecules closer and closer together, you are increasing your density as well too. Now this only happens at depth. It doesn't occur at the surface, because at the surface you just have normal 1 atmosphere of pressure, and that doesn't affect the density of seawater. Alright, so this was the end of the chemistry lecture. Let's talk about physics now.